Good evening, everyone. Can you hear me well? The Sierra Club welcomes you to this event, and it's really timely and beneficial that we have a specialist here who has studied the human mind and human behavior and has also become an influential voice in the climate debate. Dr. William Calvin, our guest today, is a professor at the University of Washington School of Medicine, and he's affiliated with its program on climate change. He's most recently the author of a book, Global Fever: How to Treat Climate Change, and he's written at least 13 other books for general audiences, averages one every 2 years. Think of that. His studies have included brain circuitry, ape-to-human evolution, climate change, and civilization's susceptibility to abrupt shocks. And he brings with him a lifetime of reflection on the great problems, the great questions of our time. He's worked on the leading edge of interdisciplinary practice. But most importantly, Bill brings some substance to what we've all come to realize, and that is that the behavioral challenge in meeting climate change is equal, if not greater, than the technical challenge of implementing the solutions that we've developed. If we don't really want to do what has to be done, and if we can't properly manage our motivation, then we surely will not succeed. Now, a great proportion of Dr. Calvin's research and writing has served to inform us about our neurophysiology, our brain, and our minds, and this is information that we need. I know from my own experience as a paleontologist that any interest in biological evolution immediately leads to an interest in climate, especially the climate history and the mechanisms of climate change, because climate, more than anything else, routinely shifts the environment that all species must evolve to match. And it could be said from the point of view that species, well, let's say it this way, that the climate is the question to which species are the answer. And the species that's best answered the call of abrupt climate change is the human species. And Professor Calvin has really fully developed this simple notion in his really wonderful book called A Brain for All Seasons, and I think there are copies here tonight. Human Evolution and Abrupt Climate Change. This is an engaging account at many levels, but none more so than in recognizing that the conditions which brought about the evolution of humanity are similar to the kind of stresses that we're imposing on the planet ourselves right now. And it adds extra meaning, I suppose, to our notion of meeting our maker. Beyond his scientific skills, there's another virtue this fine scholar brings to his work, and for me it's beautifully represented in his little story about Acheulean hand axes. These are stone tools that had more than 1 million years of application. And they're sort of disc-shaped with a sort of a sharp edge and a blunt point. Now, if you're just going to crush things or scrape things or break things, they're over-engineered. And they're too sharp around the edges to hold comfortably. You do yourself some damage if you hit things with it. So what are they? And he came up with a terrific idea. He says they're aerodynamic. They really throw very nicely. And if there's animals concentrated around a waterhole, you can probably do enough damage to knock one down and potentially capture dinner. So this kind of lateral thinking is admirable, and we'll see it on a much larger scale in his presentation tonight. In his reflections on our present dilemma, Dr. Calvin reminds us that humanity is massively stressed, and at the same time, we're actually not the perfect psychological vehicle for our own journey. And the vagaries of evolution have thrust us somewhat unprepared into our present circumstances. Now, everybody knows by now how high the stakes are for humanity. A big collapse in the food supply, flooding due to sea level rise, loss of fresh water, are likely to be attended by behaviors and practices so bad that our civil life would suffer for a very, very long time. So he reminds us that foresight and preparation and planning have become more important than ever. And practicing them is best done in the manner of a caring parent. We need to do this, live this awakened, intentional, and caring kind of life, bringing creative minds and inspirational voices like Dr. Calvin's bring towards us to help, because he brings precisely the kind of motivation we need to pursue this path. Bill Calvin's a mature voice. He brings a sharp eye of an elder to the climate table. He's not reluctant to remind us that time is short and shortening, that we have only one planet to lose, and that we cannot, no matter what our age is, leave this to any next generation. The next 12 years are of the proving ground of action, and he has some specific ideas for us to get it right the first try, and we'll hear about that tonight, I'm sure. And yes, indeed, he does acknowledge that we could fail and we should think about what we might leave to our successors in that event. Success, on the other hand, in this great quest, would be on the scale of establishing a new country or winning a great war, which gives us solid hope, really, because these things have been done before, they've been understood, they've been studied, and they can be done again. Those of us committed to this cause draw significant comfort from colleagues like Bill Calvin that see things with his kind of clarity. The Sierra Club and Dr. Calvin too, I'm sure, would both be pleased if his words strengthened our conviction and motivated our resolve. For it is our duty and our challenge and our privilege to attend to this focal matter of our time. Dr. Calvin, on behalf of the Sierra Club, the University of Victoria, and our audience tonight, welcome.
This is not going to be a beginning talk on climate change. My object tonight really is to go beyond things that you've mostly heard about and try to tell you some of the rest of it. There's two major take-home messages. One is that there are big sudden problems that tend to do the damage before the gradual changes start doing the damage. And that just like physicians in emergency rooms, we have to deal with those things. You can't just send a patient with an aspirin overdose home with directions not to take so much aspirin. If they've ingested a lot of it, those people have heart attacks, and you have to put them on dialysis to try to detoxify them quickly. We're in something of that position now with carbon dioxide. The second point here is that, in fact, our climate situation is not as hopeless as we've heard in a lot of stories from the scientific community in the last year. None of them really address the issue of cleaning things up. They simply address the issue of what will happen if we continue going the way we're going. However, zero emissions doesn't get us out of the problem. Only getting rid of the CO2 that we've already put in the air will get us out of most of the problem. Okay, so many know by now that we're overheating. Around here, you know that leads to lots of wildfires. This is just the western states in the US, but I assume it applies up here because it applies to the entire rest of the world, except they got hit before we did by about 10 years by this kind of exponential increase in fire. I could show you a plot of major floods around the world on all continents, and it would look just the same. Doubling in the 60s from what it was in the 50s, doubling in the 70s from what it was in the 60s, all the way up to the 90s, where it fortunately didn't double, it only went up 30%. Those are major changes that have already been happening. We don't really need climate models to tell us that we're in big trouble. All you have to do is to extrapolate that trend a little bit further, and you can see the kinds of difficulty that we're going to be in. Around here, you may have noticed that Mount Baker looks a little different these days. That blue line shows you where the ice came down to at the end of summer in 1985. And this is happening to all the major glaciers in the world, and the models say that all of the ice that's on glaciers like this, mountain glaciers, will probably be gone by the middle of the century. Of course, that's what we said about the Arctic sea ice too, and it's happening far quicker. You also know what warm winter times do up here. This is that mountain pine beetle that the larvae tend to live over the winter in the bark, and then they wake up in the spring and they start chewing away. Yeah, but in most winters, the cold kills off most of them. If the cold doesn't kill off most of them, they erupt so much, the bark so much, that the tree dries out and dies. And that picture at the bottom, in case you haven't seen it locally, that russet color is the color of trees that died just in the last year. By the second year, it will be entirely gray. The emissions of CO2 that you get from that happening just in BC overwhelm the emissions actually that you get from all the highway traffic. So there are really major consequences of this as we... Now, the other thing that everyone sort of knows by now is that it promises to get much worse, but the timescale is always sort of someday, mid-century, whatever it is. Unless, of course, we reduce emissions, clean cars, clean energy, more efficient uses of things, less waste, and reforming agriculture and forestry, which account for about 1/3 of emissions between them. The problem with that is that it doesn't get rid of the CO2 that's already in the air. And that doesn't go away by itself very nicely. So let's go through some exceptions here. It's the extreme events that tend to do the damage. Promises to get much worse. I mean, how would you like next year? I'll show you in a minute what I mean. And this list of what to do about it is totally inadequate, except as a way to speed up a real fix that actually removes CO2. I mean, our plans for climate action look to me more like one of these buying time therapies for late-stage cancer. Compare that to a physiological fix, the kind of dialysis for kidney failure that makes possible a near normal patient for decades. I think we've been failing to ask what a climate fix like that would look like, one that relieves many of the ocean acidification and climate problems and makes possible a near normal planet. So I'll outline a bit for you what I have in mind. Let's go through a few examples of gradual and abrupt climate change. Let's take the heat wave in Europe that killed about 35,000 people. There are two ways that you get more extreme temperatures. If you've got a Gaussian curve like this of temperatures, say the peak summer temperature being plotted for different years, there'll be cold years and hot years, and you could have an increase in the mean, which is sort of what you'd predict off of greenhouse effects and such. Gives you less cold weather in winter and less the bark beetle problem. The other thing that can happen is that you get an increase in the variability. As say, more record cold weather as well as more record hot weather. Or of course you can have both. It's this increase in the variability that has worried, comes straight out of the climate models. If you see that, it's one of the predictions. But there's also changes that are really in the mode of operation of systems that climate models basically don't handle yet because they're not detailed enough. I mean, for example, if you have a river that finds a new shortcut, say it cuts across a meander, shortcuts it, that's the kind of change in circulation that you can also have in the atmosphere, except that you don't have riverbanks to remember what last year's was like. And if you've got sort of two alternative paths for the winds to blow and it sort of switches over to one it doesn't normally use very often, you can get very dramatic changes in terms of how much rain falls where. This is what the European heat wave looks like on a Gauss curve of summer temperatures in northern Switzerland as it happens here. The coolest summer in a 140-year period was 1909, when my father was born. And the warmest summer was 1947 until the year 2003, when things really jumped off the chart. That's 5 degrees, more than 5 degrees above the mean, 17. That's about 6 standard deviations. And if that is a normal distribution, that's something that might happen by chance every 4,000 years or so. My guess is this is not just that kind of extreme of the Gauss curve. My guess is that it's a change in the circulation pattern where it's demonstrated to us that there's another way the system can work. And how often it will revisit that, we'll be finding out. But just from the standard modeling of gradual creep up, you can go through and calculate how many days are there going to be heat waves each year. Now, each place has a different number of them. If you just define a heat wave as 5C above normal locally, and then plot a map, what shows here is the number of excess days of heat wave that you would get at each location. And there are areas like where we live here where it's a week or maybe 2 weeks per year of days of heat wave compared to what they were back in 1990. But you can see certainly in the American Midwest and up above Hudson Bay, so forth, there are places that are going to have more than 3 weeks additional heat wave days. Now, heat waves are also killing coral. This is bleached coral that you see here. That's coral is a symbiotic thing with a plant part and an animal part, and the white part is the animal part with the algae sloughed off. And they do that when they're in stress, usually from temperature increase. And if the algae and the plant get back, the algae and the coral get back together within a couple of weeks and the coral survives, if it goes on for too long, the coral dies. It's just a primitive system that has unfortunate consequences. And it turns out that the heat wave in 2005 in the Caribbean, which I will be coming back to, caused the Caribbean to lose at least half of its corals. And 25% of all marine species need coral reefs to live and grow, and about 40% of the fish caught commercially use reefs to breed. So this is already a very substantial effect. The major coral reefs of the world, that's the big reefs, we're not talking about individual coral clumps here and there, those are expected just from the climate models to be like the mountain glaciers, mostly gone by 2050. Now let's talk about another kind of fairly sudden change in things that usually persists for years, and that's drought. You know, you can have an onset of a big drought within just a year or a little more, and it can persist for years. Well, all sorts of areas are getting droughts now that didn't used to get them like this. Now, I'm going to try to show you why here. In the tropics, where the heating of the ocean is greatest, there are, of course, a lot of updrafts of the warm air rising, and that brings in air from the sides and goes up. And of course, it's very humid going up, and so it promptly starts precipitating out as rain. Now, all that air that goes up has to come back down someplace. And it tends to come back down, you know, maybe 20 degrees or 30 degrees of longitude, you know, further north or south of the equator, and so you get these dry bands, such as where the Sahara is and the Kalahari Desert is, and so forth. That's just the average. All those red areas that are on the map, like around the Mediterranean and California and Australia, are regions of where it's called Mediterranean climate. And what that means is that they get rainfall only in the wintertime, but not in the summer. They have a very long growing season, and there's no rainstorm is likely to come along and ruin the wheat crop and so forth. Now, that's only because they're right adjacent to a desert. And in summertime, the deserts, that sort of pushes a bit further north, and that's why they don't get any rain, just like the rest of the desert. But in the wintertime, the westerly winds can now sneak along the top of this zone and get in and produce the rain. As you expand the tropics, you push the dry zones further away from the equator, both north and south. This is why southern Australia's Mediterranean climate zones are getting into big trouble at the moment. It is why North Africa is getting into big trouble. It is why Southern California is getting into big trouble. All these are basically consequences of the heating of the tropics. Now, furthermore, the global drought, not just tropical, subtropical areas, but all areas like up here and such. If you look at the world and ask what percentage of the world land surface is in drought at any one time, the answer used to be 15%. From 1950 through 1982, what you basically had is about 15% of the land surface in drought. In 1982, 83, it jumped up to 24%. And it stayed that way for the next 15 years. So it's a stepwise change in the amount of drought in the world. And then in 1997, it did that, jumped another 9%. So for those 6 years, we had drought that was up in the 33% territory. Now, fortunately, it came back down into the 20s. But this is the sort of sudden change that the system seems to be capable of. The computer models predict the expansion of the tropics and the Mediterranean areas getting into trouble, but they generally don't have features like this. And it's only a matter of time before we'll be able to do that kind of dynamic modeling with the resolution that it takes to get these things. But basically, the observational record is telling us that the climate can take abrupt changes that are maintained for long periods. And this is the kind of danger zone that we are now in. This is the amount of CO2 put into the air each year. Normally, it's down around, well, this is in gigatons. If you put parts per million, it's about half that. But the point I wanted to make here is that during the El Nino fires of '98, we were putting about 2 or 3 times the average into the air that year. Now, I'm calling it El Nino here for the reason that those 2 big steps took place during big El Ninos. Here's the El Nino La Nina record from 1970 to now. And what you see is several things. First of all, starting about 1976, you don't see it as well in this record, El Ninos start getting much larger and much more frequent. But the big ones, 82 there and 97, have been the ones that were associated with the big drought steps that maintained themselves. What you got to realize is that each of these lasted only about a year or a bit more. And plenty of other El Ninos, like that one in the late 80s, last for 2 years, even longer. So you have to ask yourself, what would a double duration and big El Nino do to the drought situation? Well, first of all, a lot of Amazon and Southeast Asia did burn in '97. That's why all that carbon went up in the air, either as smoke or as decomposition, CO2, rotting. But if you really wiped out much, if you did have a really bad fire and rotting season, Amazonia, at least, would not regrow as rainforest. It would regrow as grassland. And because of that permanent lack in photosynthesis capacity, our standards are 2 parts per million per year increment would go up to about 3, even if we didn't increase emissions. So something like this gets us in trouble in 2 ways. First of all, there's a big jump in CO2 if you burn off that much at once. And back in '97, it would have been about a 50% increase in the excess CO2, the anthropogenic CO2, just from that one event. And so worldwide, you would have had big climate problems developing from that. It's what I call the burn locally, crash globally scenario. And I wanted to illustrate why that is a present danger and not merely a mid-century one. And I checked my Mayo yesterday. I discovered that it's closer than I thought. Well, imagine yourself during a future El Nino, watching the flammability index and worrying about a big burn, the 50% increase in excess CO2 and the 50% speed up in others, jumping all the problems. Certainly for Amazonia, mass extinction of species, and all of the worldwide problems of collapsing governments, mass migrations, and amongst all those people trying to flee areas where there was nothing for them, you would get a lot of famine, pestilence, war, and genocide. This is not a pretty prospect of us sort of struggling along and trying to adapt to climate change. If you can have things that big happen, a lot of the human reaction to it is going to be even worse. This is the forecast from NOAA's El Nino Forecast Center that came out last week. And it's basically showing us going into an El Nino next month. It will look, the graph on the left there is for basically October, but it looks pretty much like that for July in the forecast. And then over on the right, you see the January forecast where that heated area in the Central Pacific is much larger, more than twice as large. Now, they're pretty sure in their forecast that there's going to be an El Nino. They don't know how big it's going to be from the forecast method. But the outlier amongst the various models they've made does have it being as big as the 1982 El Nino. So we'll see as this develops. Now, it turns out you don't need a big El Nino to do the damage. It turns out that the 2005 tropical heat wave that killed all this coral also did a job on the Amazon. This is the Amazon rainfall over the years, and you see that at the second arrow there in the middle, the 1997 rainfall deficit. And over on the right edge, you see 2005, about 50% greater deficit in rainfall. I'm told that 2007 was very bad too. So even without the El Ninos parking a big high-pressure system over the Amazon basin in Southeast Asia at the same time, there's big damage like this possible. Even if it doesn't burn, a lot of stuff dies and it rots, and the CO2 goes in the air just a bit more slowly. So I've shown you actually 6 different things that constitute my major worries. From '76 through 2005, we had 4 abrupt climate shifts. We had a 1976 shift to El Nino dominance instead of La Nina dominance, you see there at the top. You see the ramp up in land temperature starting in '76. You see the drought steps in '82 and '97. And then we had these 2 near-miss episodes for burn locally, crash globally. That's 6 in 30 years. So that's the chances of getting, a couple more in the next decade, I would say would be pretty high. And you have to remember that the excess CO2 was a lot lower back then than it's going to be in the next decade. In fact, it's going to be about twice as high in the next decade as what it was in '76. Now, there are likely a lot of other threats, climate surprises, as the fever rises. I'm only listing the recent surprises that I discover in the literature. And I'm listing only one of the many possible abrupt change threats that have been identified. There's various papers in the literature now on the dozen and more such things around the world that could make a big change in world climate. So, trouble is, with the ones so far, we have survived, but it's sort of like heart attacks. They can range unpredictably from being minor to being catastrophic. And I think we really must reframe our climate policy to focus on a quickly implemented climate fix and have the longer range plans follow from it rather than overshadowing it as it does even today amongst climate scientists. We've already had 2 near misses separated by only 6 or 7 years, and I think we now must back out of the danger zone in a manner that is both swift and sure. Now, when you hear the words abrupt climate change in most science stories of the last year, it actually is referring to the situation without engaging in this carbon removal from the atmosphere. Partly it's the way that modelers work. You don't want to throw in a fudge factor like taking carbon out of the system that you don't know whether it will be implemented or not, and you just go on the physics of what will surely happen if you continue the trend. But there really are things that one can do in the way of large-scale carbon removal that would actually be a possibility for putting the genie back in the bottle, essentially removing, for the sake of argument, all of the excess CO2 and put it back into long-term storage and do it in about the next 20 years. The total debt by 2030, extrapolating from what we're already putting into the air, means that we're going to have to take about 600 gigatons out. Now, a pile of coal as high as Mount Rainier would have in it about 150 gigatons of carbon. So it's about 4 Mount Rainier units we have to sequester. This is where that comes from, just integrating the area of the emissions curve, going back to 1750. I'm just showing you 1950 on. And the extrapolation for the next 20 years is just based upon the last 10 years of emissions, which are, of course, 4 times steeper than they were back before them. That is to say, reducing emissions has not only been a failure, but it's gone fourfold the other direction. So 600 total, and this is the same thing on a different reduced scale, but it's showing you all the drawdown that you have to do. That is to say, you have to take out, on average, 30 gigatons each year. Now, emissions are currently 8 or 9 gigatons adding. So the first part of that well there is just canceling out the continuing emissions, and the rest of it is actually drawing down what's in the air and in the surface layers of the ocean, and to some extent the soil. Now, how are you going to get this much carbon? Freeman Dyson is fond of saying something to the effect of, well, you just grow a lot more trees. And since the trees take out about 40 gigatons a year of carbon, in terms of putting it into storage in the form of wood, you could probably double the forests and get what we need. The only trouble is that it's really a non-starter. The climate forecast, first of all, you have to find the space and the water to grow all that. And secondly, the climate forecast happens to be for more drought and high wind, just the thing to burn down all of your new trees quickly. So we really while as scientists we tend to focus on one thing at a time if we can, you just can't go around ignoring all the other dimensions of the climate problem in planning a retreat. So there are schemes for taking CO2 directly out of the air. They're basically like the systems that are used in submarines for scrubbing CO2. But finding the power to run such a giant new industry, I don't think it's in the cards for the next 20 years. But it's really not necessary to remove CO2 directly from the air in order to reduce its concentration there. That's because of the carbon cycle. Photosynthesis every year is taking about 210 gigatons of carbon out of the air, and it's creating organic carbon molecules out. You know, starches, sugars, all the things that cells then make from it, so on. And at the other end of the carbon cycle, a lot of CO2 is put back into the air via respiration, and secondly, decomposition of cells as they die through burning or rotting. And if that totaled 210, then the atmospheric concentration wouldn't change very much. If you intercept some of the decomposition carbon before it reaches its usual destination, then, let's try it again, what you're doing is drawing down the CO2 in the atmosphere. That's what we want. So basically, I'm going to focus on ocean because it's the only place that has the needed growing space and doesn't conflict with growing crops and uses of water for people. The problem is growing that much algae and then sequestering it in the deep ocean. Here's a brief diagram of what the ocean part of the carbon cycle looks like. There's a land part and a rock part as well. But in the air we're currently adding through deforestation, the rotting and burning of the timber takedown, about 2 gigatons of carbon per year, and about 8 or so from fossil fuels and making cement, which is, you know, limestone is sort of an honorary fossil fuel. Into the ocean's absorbing about 92 gigatons, and the respiration and decomposition processes are releasing back about 90. So the oceans are absorbing a net of about 2 from this. Now the oceans are divided into, to simplify it, 2 layers. There's the surface layer called the wind-mixed layer. And at the bottom of it is the thermocline. And basically, the winds drive the waves to churn all this water. So as you sink a probe down through it, the temperature stays pretty constant and the oxygenation stays pretty constant. Then you start getting down to the bottom where it starts getting colder and other characteristics start changing, and you start getting into the depths that slowly circulate. And that's where a lot of organic carbon descends to. Feces that are big enough, fecal pellets that are big enough to sink. If they can make it through that surface layer in a couple of days without decomposing, wind up being in the sequestered carbon. The depths, however, are about 98% of ocean volume, so this is sort of like the the rim of the orange or maybe the apple peel in terms of things. Okay. Basically, 48 gigatons are being photosynthesized. You get 37 going back out for respiration and rotting. And the difference between them, 11, sinks either as fecal pellets or as the larger cell debris. But a great deal of it really becomes dissolved organic carbon that just won't sink. But these wind-mixed surface layers contain a lot of this organic carbon, just waiting for the bacteria to use it for food. And within 40 days or so, it's carbon dioxide back into the air. So our goal, as you see in that box up there in the corner, is to take that 90 gigatons and reduce it by 30, so that we're only putting 60 back. And basically, there's not much hope of getting at the respiration part of it, but the composition part of it is interesting. For one thing, besides the fecal pellets and so forth dropping down, the carbon in the surface layers is carried down into the deep layers at a few places on the globe. This so-called bulk flow, I suppose the oceanographers probably call it vertical advection, but in physiology it's called bulk flow. This carries down really quite a lot. Go back here, well, it doesn't show there. Oops, here we go. Okay, here's the complete diagram. And what you see here is that I've added over here this bulk flow downwards that basically takes some of everything that's in the surface layer and moves it down. So it's moving down a lot of that dissolved organic carbon, of which counts for most of the carbon that's in the mixed layer. That is to say, it's about 100 to 1,000 times more than the living matter of plankton and so forth. But you're moving the whole thing down, and one of the interventions would be intervention B there to simply pump more down and get your 30 additional gigatons that way. The other is to increase the number of fecal pellets and cell debris that sink down. Intervention A over on the left shows you that you would need 4 times as much sinking to do that. As to say, the current 11 you'd really have to triple to get into the right territory. And that's worldwide. So that may not work, and that's probably why the iron fertilization kinds of strategies won't work, even if you could get them working better than they are now. It's simply too small to do the job, as is most everything else. But the prospect of sinking a lot here is aided by the fact that that's what sunk most of the anthropogenic CO2 already. This is a map showing you the North Atlantic, and that just shows you the inventory of the excess CO2, so-called anthropogenic CO2, that has already been deeply sunk in the North Atlantic. That's why there's such a hot spot up here. Now, if you look in cross-section down here, so this is sea level going clear down to the seafloor in the North Atlantic, from the equator up to about 30 degrees is what I'm showing you here. And you see that the thermocline would be here at about 100 meters. This would be 1,000. So just below the thermocline is where a lot of it's residing in the rest of the world and in the southern part of the North Atlantic. But what you get in the North Atlantic that you don't get anywhere else is there's this enormous amount right here, and that's what's causing all this up here. So this meridional overturning current that carries so much of it down, just sort of an automatic flushing mechanism, is, of course, the thing that when everybody talks about the Gulf Stream failing, this is what they really mean. The major sinks are up in the Greenland Sea above Iceland, and also in the Labrador Sea down here, and together they account for about 20 times the flow of all the rivers in the world. So it's a lot. And if you were fertilizing anywhere near the whirlpools that sink this, you could in fact get a lot of additional carbon carried down into the depths as dissolved organic matter and as the plankton themselves. So that's one thing we could think of. Now, one of the ways you can fertilize, besides going around and like a grass seeder and throwing out nutrients, which I don't think will work, you can always pump up nutrients from below, because 100 meters down there are lots of nutrients just hanging there, and if you pump them up to the surface, you will presumably give it what it needs. Now, you could do that with windmills that float like this, same sort of thing they're planning offshore here for doing electrical power generation. Or you can use a very simple kind of pump that's shown on the part B of the figure here, which is just basically a big open tube that hangs, say, 1,000 meters down into the depths, and it bobs up and down with the waves. And it's got a trapdoor valve at the top. So that while it's sinking, nothing moves in and out of the pipe very much. But when it's hauled back up, the trapdoor opens, and you basically extrude surface water into the depths. You don't literally extrude it, you just move the pipe away from it and leave it there. So this is the sort of very simple kind of pump that you could imagine, making and deploying for $1,000 a piece or something, that you could try to use to manipulate some of these things, both for hauling up nutrients, you just make the trapdoor go the other way, or for pushing water down. Now, you're not limited to using the North Atlantic downdwellings to get it down. You can always pump surface water down. And there's lots of places in the world that you could do that. Basically, you'd pump nutrients up, and then downwind, down current, you would put the pumps to pump down plankton. And since a lot of the nutrients will produce plankton that fish will consume and so forth, this will be a great boon for fishing. And one can imagine plankton plantations like this designed to maximize what you sink, but also providing the fishing industry with a chance to improve upon the situation they're currently in. The natural fish populations, even in the areas where the catch is managed so it doesn't sink any further, it still sinks 70% down. So any area that's being managed for a sustainable catch has also reduced the fish biomass by 70%. So there's a lot that you can make back up to get back to normal. Now, in terms of calculations about how big this operation has to be, I can only show you, if you treated it like an algaculture problem, the way the biodiesel folk would do it, you might estimate that you can get about 55 grams per square meter of algae every day, dry weight. And if half of that's carbon, it would take about 10 to the minus 4 square meters of ocean surface to sequester a gram of carbon every year. So to sink our 30 gigatons of carbon yearly would require about 0.8% of the total ocean surface, about the size of the Caribbean. But in the open ocean, it's not like algaculture. The algae are quickly consumed by zooplankton before you get at them. And so this can't really be directly compared. However, would be sinking the entire carbon soup. Not only the algae and the zooplankton and the debris and the feces, but that enormous amount of dissolved organic carbon. And that's what makes the whole thing look like it's even more feasible than the size of the Caribbean. It'd be much smaller. Now, the question to me is whether we could do this in time, and there's lots of concerns for that. My first reactions was we'd never get international agreement fast enough. Law of the sea considerations and such, but in fact, continental shelves are within the exclusive economic zone of all the adjacent nations, which will have a strong interest in new fisheries. And continental shelves in the most productive latitudes currently for photosynthesis belong to relatively wealthy nations. I mean, their independent initiatives could quickly establish a lot of plankton plantations. And in fact, the first mover advantage might even encourage them to compete in creating them. What about operating costs? Well, first of all, we're not having to harvest anything. We're sinking it on the spot. And the continuing costs would be mostly for maintenance, which could prove substantial, monitoring, and perhaps for adding some micronutrients to fish. But you have commercial fishing fees that might, in fact, keep it running. Concerns about how expensive it is. I can't tell you how expensive it is because I don't know how many pumps you need. It's really going to take trial field demonstration projects to work this out. But bank bailouts have been extremely expensive, and it's probably on the order of something like that spread out over the years. There's a question of you put CO2 down there, but it comes back up when? The circulation of the oceans carries down a lot of water from that sinking stuff. That's what carries oxygen down to the bottom of the ocean. The bottom of the ocean's got as much oxygen as the surface. And then it also comes back up in a number of places around the world, best known for being good fishing grounds, because they carry up nutrients and stimulate growth. Well, it takes 400 to 1,600 years, basically, to make the loop. And so what you're going to have is you're not going to have, we might inject all the CO2 in 20 years, but it's going to come out smeared out in time over 1,200 years at very much lower peak levels because of that. So there is a chance of reducing the harm greatly so that the people of that century, that millennium, are not hit as bad. There are lots of objections about this, but let me really sort of finish with this one. Why the 2030 rush? Well, the current 350 gigaton accumulation of excess carbon could double by then. I mean, 250 is what I was showing, but in fact, there's methane from Siberia and Alaska from the permafrost melting that I was not included in that figure. And there's lots of reasons to think that just 20 years is going to get us into double trouble. With 6 sudden shifts or near misses in only 30 years, it would be prudent to expect even more surprises, even as we're doing this. Just reminds me of the way the US finally got into World War II. FDR used the metaphor of a 4-alarm fire up the street that needed to be extinguished immediately, whatever the cost. In contrast, our current climate response is mostly a re-emphasis of the old virtues. Clean air, clean energy, sustainable agriculture, better efficiency, less waste, longer-term thinking, which I've been preaching forever, but all those things that might have kept us from painting ourselves into the corner. But we are already in the corner, and all those things, without a big removal project, are not going to get us out. They don't really constitute adequate treatment for climate disease. I think I told you that before. Undertaking such a large project is said to require an easily understood goal, say, go to the moon in a definite time frame in this decade, said JFK. Suggesting a slogan something like clean up CO2 before 2030, if you don't like, put the genie back in the bottle. But I think acquiescing in a slower approach is really like playing Russian roulette with a climate gun. This is a politician of 400 years ago. Public interest requires doing today those things that men of intelligence, goodwill would wish 5 or 10 years hence had been done. I think we've got substantial prospects. We have the intellectual and industrial wherewithal to do a great deal of this, and I just sort of leave this running for you to show you basically the power of what's going on every day. This is just airplane flights over a 24-hour period. You see the sunrise creeping through Europe at the moment. It's going to explode into flight activity. And when it reaches New York, you'll see the same thing. I mean, this is the kind of business as usual atmosphere we're operating in. As we saw in World War II, you change to a war footing to do something. Projects whose development would ordinarily take 30 years can be done in 2 years. So thank you very much, and I'll be happy to take some questions.